Okay, welcome to part 5 of the OwlBot project, where we're going to be adding mechanical movement to our prototype circuit. So for the goal of this part of the OwlBot project, we're going to have the Arduino Uno control the solenoids to activate on and off continuously when motion is detected by the peer sensor we added in part 1 of the OwlBot project series. And then we want to have a DC motor spin a propeller when motion is detected by the peer sensor. So by the end of this part of the build, we'll want our prototype circuit to play the MP3 player file with the owl sounds on it to the dual speakers we added to our prototype in part 2 of the build. We want to flash both the LEDs that we're using as the OwlBot's flashing red eyes that we added to our prototype in part 3 of the build. And we want to activate the 2 solenoids and have the DC motor spin its propeller that we're adding to our prototype in this part of the build. So as you can see here, we have our prototype circuitry set up. This is that peer sensor that we added in part 1 of the build series. You can see the Arduino back here, the 2 speakers and MP3 player back here that we added in part 2 of the series, and you can kind of see the 2 LEDs that we added in part 3. And for this part, here's the 2 solenoids we'll be adding to the prototype circuit, as well as the DC motor with the propeller on the shaft of the DC motor. So by the end of this part of the build, we want to have the LEDs flash, the owl sounds to play, and we want both solenoids to go off and the DC motor to spin the propeller on its shaft once motion is detected by the peer sensor that we added in part 1. So let's go ahead and talk about the solenoids. I'm using these 2 6-volt push-pull linear solenoids. The technical specs that I was able to get for them claim that they have an electromagnetic push-pull force of 50 grams, or about 1.76 ounces, which is equivalent to 0.11 pounds. We need 2 of them to control both the faux wings of the OwlBot we'll design later on in this project. So we're going to use the 2 solenoids to control the movement of those wings we'll design later. I did perform some rough preliminary tests on how much force these particular solenoids that I'm using were able to provide, and I was quite impressed for these little tiny solenoids on what they were able to do, especially based on what I'm using them for here. I'll go ahead and provide that short video clip showing those tests right here. So I was able to get the solenoid to lift without any assistance a 9-volt battery with its snap connector, which, as you saw, was a combined weight of approximately 1.4 ounces according to my measurements. I think with what I have in mind on how I'll make the wings and from what material the wings will be made of for this OwlBot project, I think these solenoids will work just fine to be able to move those. The wings will be fairly lightweight. They're going to be made, I'm thinking of making them out of maybe a thin wire and somehow connecting that wire to these solenoids, and that wire providing not only structure for the feathers that I'm going to use, but also to help in the mechanical movement that we'll need to make those feathered wings move. And I'll show you those feathers that I've already ordered here. This is the package of those feathers. I thought these would do pretty well and kind of look like they could be owl feathers. I'm not sure what kind of feathers these are, but I'll use these. I got these off of the rainforest store, and we'll use these feathers later when we build those wings later in the project to add to our owl figure that we're using. So hopefully that will all work out according to plan. I have not built those wings yet, so I have a kind of a rough idea, so just hoping that that's going to work. I think these solenoids will work out fine in moving those things. The only thing I'm really worried about is the type of wire that I'm going to use and how I'm going to use the wire to create the structure for these feathers and getting them to attach to the shafts of the solenoids. So I don't really know how I'm going to do that yet, but we'll get to that part later on in the project. So as for the DC motor with the propeller, I'm using this to add more motion for the OwlBot. It's not necessary if you don't want to add this to your prototype, but I wanted to do so in order to create more movement for this OwlBot figure. And the DC motor that I'm using, I managed to scrap it off of some other device in the past long ago, and I don't remember exactly where from. I think I got it from an old printer maybe, but it doesn't really matter. You can use any old DC motor that you can find, one that's small enough to use for the project, obviously. But you can also, if you don't have any DC motors lying around, you can get small DC motors from like motor hobby kits or hobby motor kits. And I'll provide a link down in the description below in this video of the exact motor kit that I've actually purchased in the past for my daughter. So you can check that out if you'd like. And just so you know, any links that I provide, they may be affiliate links, and there may be some form of payment that I receive from those links. So just to let you know. So as for the parts list and tools used for this project, I'm going to go ahead and have all of that kind of scroll down on the bottom of the screen or show up at the bottom of the screen in kind of a Bob Ross style showing of the material that we're going to be using for this part of the build. So as I'm talking, all that will be showing at the bottom. So you can take notes on that. If you want to see the full parts list and the tools used for this project, I'll leave a link down in the description to the website that will take you to the full detailed list of those parts and tools used for the project. So in prototyping the circuit for this part of the build, looking back on part 3 of this build series, where we made all the connections needed for the red LEDs we added to our circuit we then needed to create the code to have those LEDs flash when motion was detected by the peer sensor that we added in part 1 of the build series. And then now we need to add this prototype to this prototype a pair of solenoids and a DC motor that will provide the mechanical movement for our OwlBot. Also, we need to update the code and add to it the functionality we need to get the solenoids to activate and the motor to spin the propeller when motion is detected by the peer sensor. If we remember back on part 4, we upgraded, or we actually modified, the power supply to our OwlBot prototype circuit to power the new power-hungry devices. We're adding in this part of the build, we added another 9-volt battery supply made up of 6 AA batteries to our prototype. I have it set back here so it's kind of hard to see. We'll use this upgrade to power both the solenoids and the DC motor. Our original 9-volt battery supply we're still using to power the Arduino and the devices we've connected to it thus far in the build. So remember, in TUDIY, there's a built-in 9-volt battery power supply controlled by this switch here. And in talking about TUDIY, I will be using the ultimate DIY 3220-point breadboard that was made from a separate project. That's this setup right here. I've called it TUDIY for short, so that I don't have to keep repeating the full phrase, the ultimate DIY 3220-point breadboard. I just called it TUDIY for short. So that's what I've been using throughout this build series. So don't worry, even though I'll be discussing how to make connections on TUDIY throughout the following prototyping steps, I'll provide images on how to hook up the items on a generic breadboard so you can still follow along. So if you recall, we've been using an Arduino Uno for our prototype circuit to help control some of the devices that we've added to our circuitry. And before we get started with anything for this part of the build, we first need to go over the Arduino Uno's Atmega 328P microcontroller. If you give me a moment, and if I can just reach over here, you can sort of see that microcontroller here. That's the Atmega 328P microcontroller used by the Arduino Uno. And like I said, we want to kind of go over its absolute maximum ratings. I think I said that. I'm not sure if I did now that I think about it. But what we want to do is go over its absolute maximum ratings to gain an understanding of what we need to do to hook up our components properly to prevent damage to the Arduino Uno and its microcontroller. So I'm going to put this table up on the screen, and if we have a look at the table on the screen, we see that the values within it are the absolute maximum ratings for the I/O pins, or the input-output pins of the Arduino Uno's Atmega 328P microcontroller. This table came directly from the Arduino website, and I'll provide the link to this down in the description below. And I think this table was on page 302, if I'm not mistaken. I'll put the page number down in the description below as well, so it'll help you find where it's at more easily on that data sheet from the Arduino website. So looking at the values, we can determine what we're limited to based on the microcontroller's ratings. What we want to focus on are the following: the DC current per I/O pin, or per input-output pin, which states that that is 40 milliamps, and the DC current VCC, or the input voltage, and GND pins, or the ground pin, and that states that that is 200 milliamps. The data sheet is telling us that the DC current from each of the I/O pins, both analog and digital of the Arduino, is limited to 40 milliamps. The DC current to the VCC and ground pins are limited to 200 milliamps. The data sheet also states that stresses beyond these listed ratings may cause permanent damage to the device. So these are a few things that we must keep in mind as we're moving forward in prototyping our circuitry. So there's a number of different ways to power the Arduino, and that's all explained on the website for part 5. This part of the build series, I'll provide the link to that page on our website down in the description of this video below. But I'm using an external power source, and that's the 6 AA battery pack that I showed you earlier. That's back here, you can kind of see it, and that's what we added to our prototype circuit back in part 4 of this build series. So let's talk about adding the solenoids. So each of the solenoids that I'm using have 2 wires coming from the coil, or from the solenoids coil. So if I pick up one of these, you can see that there are 2 wires coming from it. Each one has 2 wires coming from the coil of the solenoid. And to make the temporary connections from the solenoids to the breadboard, I chose to use test hook clips that are spring-loaded to make secure connections to the wire ends of the solenoids. And you can see them here. Let me grab another one so we can take a close look at that. Here is a test hook clip here. You can see that on this, there's 2 different ends, and on this end, this is the spring-loaded hook, and you can see if I move the light over here just a second, there's a hook at the end right here, and it's spring-loaded, and we use this end to hook onto the wire, or one of the wires of the solenoids. And then the other end has this DuPont male connector end that allows us to pin this in into one of the points or holes into the breadboard. So let me move the light again and then focus more on our setup here. And you can see that if I pick up this solenoid here, it has a blue and a yellow test hook clips on them, and each end, or each of the wires, have the spring-loaded hooks connected to the end of the wires. Sorry, I only have one hand free at the moment. I'm going to put this back on the board. And the other ends are connected in the points or holes on the breadboard, as you can see here. I'm not going to remove them because they're all connected to the circuitry here that we'll discuss later. So we're going to focus now on how to control the solenoids with the Arduino. When using devices like solenoids on low power devices like an Arduino, we can't just hook up the wires of the solenoids directly to the pins of the Arduino and expect everything to work. Solenoids require higher voltages and currents than a microcontroller alone can provide. The solenoids that I'm using for this OwlBot project are a generic brand that was ordered from the Rainforest store online. There was not a lot of info on the solenoids except for the supposed push-pull force that they had and their voltage requirements. These, like I said, are 6-volt push-pull solenoids with a pull force of approximately 1.4 ounces, as was tested previously. In order to find out how much resistance these solenoids have across their terminals, I took my multimeter, one like this. This is just a generic multimeter. I took my multimeter and I made a reading across each of the wire terminals using the 200 ohm setting on the multimeter. I gotta look here. So 200 ohm setting right here on this multimeter. If you could see that. There we go. Now I'm focused in. So I use this on this multimeter, the 200 ohm setting, to take that measurement. And if I grab a test solenoid real quick, I'll show you how I did that. Well, I don't seem to have a test solenoid, so I'll have to take this one off of here, and I'll just put it back on in a minute. So what I did, in order to test the resistance across each of these solenoids, I took the two ends, the two wire terminals coming from the solenoid, or coming from the coil of the solenoid. I took a black end, or I took my black test wire from the multimeter to one of the wires, it doesn't matter which one, and I took the red one to the other wire terminal of the solenoid. So I have my solenoid here with my test terminals from the multimeter here. I kind of want, well, I'll just hold it, I guess. And I turned my setting onto 200 ohms. And for this particular solenoid, you can see I'm getting a reading of 6.4 ohms. So that's all I did to get the resistance readings across each of these two solenoids that I'm using for my prototype circuit. Okay, now I have that solenoid hooked back up and we can continue on. So like I said, in order to find out how much resistance the solenoids have across their terminals, I took the multimeter, I made the readings across each of the solenoids terminals using the 200 ohm setting on the multimeter. We'll need this information later to measure about how much current draw the solenoids have. And as you can see here, the following are the readings I obtained from each solenoid. You can see on solenoid number 1, I have a reading of 6.3 ohms. And then you can see on solenoid number 2, I got a reading of 6.2 ohms. So with this information, how do we control these solenoids with an Arduino? We need a way to control the on-off switching of the solenoids, and we want to control it with the use of the Arduino we're using for our project. But we can't just connect the solenoids to the pins of the Arduino, because solenoids require higher voltages and currents than a microcontroller alone can provide. So to control the solenoids using the Arduino, we need to incorporate some extra components to our circuitry to allow us to perform the tasks we ask the Arduino to do, like switching on and off the two solenoids we're using for the OwlBot project. But what do we need to do to make all this work? This looks like a job for some MOSFETs that you can see here on the prototype circuit on TUDIY on our breadboard. And I'll show you a close-up of all of this circuitry in a little bit in the video, but for right now we're just kind of going over of what it is that we're trying to do, what we need to do, and then also later I'll provide some images of some schematics and other things and close-ups of the components that we're using for this part of the project so that you can get a closer view of it. And also you can go over to part 5 of the build of this OwlBot project on our website. I'll provide the link to part 5 of the build that we're currently doing right now down in the description of this video below. But like I said, we're using MOSFETs to control the solenoids. To give the Arduino the capability to control the solenoids with its I/O pins, we will use the help of an RFP30N06 MOSFET, as you can see one right here on the screen. Now, next I'm going to show the schematic and details, and you can see that it's shown here and it explains how we're going to make our connections to the Arduino and the solenoids using that RFP30N06 logic level N-channel enhancement mode power MOSFET. The schematic shows both solenoids used for this OwlBot project, solenoid 1 labeled as X1 and solenoid 2 labeled as X2. Each solenoid is connected across a diode, D1 and D2, that acts as a flyback diode. Each of those diodes are placed in reverse bias through from the plus 9-volt battery supply to the drain or D pin of the RFP30N06 MOSFETs. That's Q1 and Q2. The flyback diodes are essential for protecting the circuit from voltage spikes generated when the solenoids are turned off. For the source or the S pin of the RFP30N06 MOSFET, we're just going to tie it straight to the negative supply or common ground of the circuit. The gates or G pin of Q1 and Q2 are tied to the digital pins of the Arduino Uno, pin 7 and pin 8 respectively. Digital pins 7 and 8 of the Arduino will provide the voltage we need to turn the gate of each MOSFET on. When motion is detected by the peer sensor we added in part 1 of the OwlBot project, we'll tell the Arduino in code later to activate the solenoids, pulsing them on and off continuously for an amount of time. Resistors R1 and R2 are both valued at 10 kiloohms. Both are tied from the gate to ground and both act as pull-down resistors to discharge the gate of each MOSFET when no voltage is applied to the gate. The gate of a MOSFET acts as a capacitor. If we don't have a path to ground to discharge the gates, then the MOSFETs Q1 and Q2 may not turn off completely. So having a pull-down resistor at the gate of the MOSFET ensures that the MOSFETs Q1 and Q2 turn off. You can learn more about how MOSFETs work and their applications on our website at the link provided in the description of this video below. Okay, now that we have this information, we want to calculate solenoid current draw. So we're going to be calculating the solenoid current draw. Earlier I mentioned that I took some resistance readings across the terminals of each solenoid that I'm using for this OwlBot project. I also took a voltage reading of the 9-volt battery pack made up of 6 AA batteries we added to our prototype circuit in part 4 of the build series, using the multimeter, and obtained a reading of 9.48 volts. Taking the average of the 2 resistance readings earlier from the solenoids and using Ohm's law to calculate the current we should be seeing through the solenoids and through the drain and source of the MOSFETs, we get a value of 1.5 amps. With a current this large, there's no way we could have controlled the solenoids by just hooking them up directly to the Arduino. We must use the MOSFETs. So now we need to discuss about adding the DC motor with the propeller. The reason why I'm including a DC motor with a propeller on its shaft to the OwlBot project is solely to add more movement to the finished product. Once we have everything in place on the OwlBot body, this guy right here, the only thing that moves other than the propeller on the motor shaft is the owl's wings via the solenoids. So the finished OwlBot will end up making sounds by the MP3 player and the 2 speakers that we added in part 2 of the build series. It'll have its flashing red LED eyes that we added in part 3 of the build series. And then it'll have the moving wings and the spinning propeller on the DC motor to help scare off unwanted critters that we're doing in this part of the build series, or that we're adding to our prototype circuit in this part of the build series. So if you don't want to include the DC motor with the propeller on your OwlBot, then by all means, you don't have to feel like you have to. You can just omit this part of the project if you like, and just stick with the 2 solenoids that will control the wings that we'll design later on in the build series. and you could just do that. Otherwise, let's just continue with how to control a DC motor with an Arduino. So how are we going to control a DC motor with an Arduino? Like the solenoids we're using on our OwlBot prototype circuit, to add a motor to the circuit and connect it to the Arduino, we're going to have to incorporate some extra components to our circuitry to allow us to perform the task we asked the Arduino to do, like switching on and off the DC motor. Again, this looks like another job for a MOSFET. So what we're going to do is use a MOSFET to control the DC motor. When using a device like a DC motor on a low power device like an Arduino, we can't just hook up the wires to the DC motor directly to the pins of the Arduino and expect it to work. DC motors require higher voltages and currents than a microcontroller alone can provide. The DC motor that I'm using for the OwlBot project was hacked off some other device that I can't recall off of what from anymore. But the only thing that I know about the DC motor is that it's a Mabuchi motor and that it's made from China. I'm guessing that it's a 12-volt motor. I'm not absolutely sure about that. Running it off a 9-volt AA battery pack supply for seconds at a time is probably totally doable for this project, so everything should work out just fine. The type of MOSFET that I'll be using to control the motor is an IRF 840 power MOSFET, as you can see right here on the screen. The schematic and details shown here explains how we're going to make our connections to the Arduino Uno and DC motor using the IRF 840 N-channel enhancement mode MOSFET. The schematic shows the DC motor M1 used for this OwlBot project. One terminal of the DC motor is tied to the positive 9-volt AA battery pack supply, and the other terminal of the DC motor is tied to the drain or D terminal of the IRF 840 MOSFET or Q3. The DC motor being used for this OwlBot project is a brushed DC motor, so I've placed a 100 nanofarad or 0.1 microfarad shunt capacitor or C1 across the terminals of the DC motor for a few important reasons, of which you can read about from the link to our website for part 5 of the OwlBot project found in the description of this video below. Also, adding a capacitor across the terminals of a brushed DC motor is good practice. For the source or S terminal of the IRF 840 MOSFET, we're going to tie it straight to the negative supply or common ground of the circuit. The gate of Q3 is tied to pin 9 of the Arduino Uno. Digital pin 9 of the Arduino will provide the voltage we need to turn the gate of the MOSFET on. When motion is detected by the Pierce sensor we added in part 1 of the OwlBot project, we'll tell the Arduino encode later to activate the DC motor, pulsing it on and off continuously and simultaneously with the solenoids for an amount of time. Resistor R3 is valued at 10 kiloohms and is tied from the gate to ground. This resistor acts as a pull-down resistor to discharge the gate of the MOSFET when no voltage is applied to the gate. The gate of a MOSFET acts as a capacitor. If we don't have a path to ground to discharge the gate, then the MOSFET Q3 may not turn off completely. So having a pull-down resistor at the gate of the MOSFET ensures that it turns off. You can learn more about how MOSFETs work and their applications at the link in the description of this video below. So if you're not using the ultimate DIY 3220-point breadboard, or AKA TUDIY, for this project, and you're using some generic breadboard, here I'll provide the solenoids and DC motor connections schematic so that you could see how to make all those connections to any old generic breadboard. I'll also provide the link to this image of this schematic shown, as well as all the other images and the schematics that have been shown in this video down in the link in the description of this video below. So now that we have everything hooked up to our prototype circuit on our breadboard, the only thing that we need to do now is to program the Arduino to activate the solenoids and to spin the propeller on the motor. But before we do that, I'll just take a quick video shot of everything up close without any talking. That way you can kind of see everything up a little closer, and we can kind of take a detailed up close and personal view of everything so that you can kind of gander around before we get into talking about the programming of the Arduino. Okay, now we're on to programming the Arduino to activate the solenoids and spin the motor. Now that we've properly made our connections for the solenoids and DC motor on the breadboard, we can now update our code from part 3 of the OwlBot project build series to get the Arduino Uno to activate them when motion is detected by the peer sensor. So as you can see here, I'm on the MOSFETs website on the How to Make an OwlBot, the Bird Intimidator Part 5 Mechanical Movement page. Again, I will leave the link to this page on our website down in the description of this video below. But if we continue to scroll down into the table of contents here, sort of at the top of this page, and we click on the section titled Programming the Arduino to Activate the Solenoids and Spin the Motor, it'll take us straight down to this part of the blog post that shows the full code or the full Arduino code listed here. And if you'd like, you could directly copy this code by clicking this icon here, and the check mark confirms that you've copied it to your clipboard, and you can paste it into your Arduino IDE on your computer and have everything right there at the click of a button for you. Or you can scroll down a little bit farther and you can click this little ad banner here. That's our ad banner for the website, and it's to our GitHub account. And if you'd like, you can click here and it'll take you straight to our GitHub page here, where you can find the OwlBot Part 5 code here. Just click on that and click on OwlBot-Part5.ino, and you can see this is the code right here. So if you'd like, you can go to the GitHub account and then you can copy the raw file here, and that is all there at your disposal, or again, you can copy it from here. So let's move down a little bit further here where the code is actually explaining the parts of the code that is new or that has been updated since the last that we updated the code, which was back in part 3 of the OwlBot build series. You can see here that the first thing that we discuss is on lines 69 and 70. We've added 2 new variables called left wing and right wing. If I go back up into the full code here and we look at lines 69 and 70, we see those 2 new variables here in the code called left wing and right wing. So going back down to our explanation of this part of the code, we can see here that these 2 variables arbitrarily represent the left and right wings of the OwlBot, or the 2 solenoids used to control the wing movement. So that's all that we've added anew to our code since we updated it last in part 3, or at least that's what's new so far in reviewing what's new in the code or updated in the code. And it just literally means that we're naming these variables the left wing of the OwlBot and the right wing of the OwlBot. And we've assigned the left wing to pin 7 of the Arduino and the right wing to pin 8 of the Arduino. So there's no political innuendos here. They're literally used for the owl's wing orientation. So come on, just chill. I mean, can we all just chill out and be excellent to each other, dude? So just moving on, we see here that for lines 71 through 73 that we've updated the code or added to our code these new lines, and 71 being an unsigned long for 2 different variables called prev time 1 and prev time 2, meaning previous time 1 and previous time 2. And we've set that equal to millis, and we're going to use these variables later for some multitasking. We have these other 2 long variables named time interval 1 and time interval 2. We've set time interval 1 to be equal to 250 and time interval 2 to be 750. And these values will represent the times in milliseconds that we'll use later on in the code. And if we look down here, we can see that it explains that prev time 1 and prev time 2 variables will be used in the code later to mark 2 previous times that we'll need for multitasking later. And it says here that we need multitasking in our code to be able to run multiple devices or components on our prototype circuit simultaneously, such as when the peer sensor detects motion, the MP3 player plays owl sounds, the 2 red LEDs flash, the 2 solenoids activate, and the DC motor activates all simultaneously. So in order to get all that to occur at approximately the same time and all activate around the same time, we're going to be using something that's called multitasking in Arduino. And you can click this link here that'll discuss more about what multitasking is. And if you look up into the references here that's on the page, I actually referenced this Imrit Aryal on his YouTube page, or on his YouTube channel, where he had a video titled "How to Do Multiple Tasks in Arduino," and he made an excellent video on that explained how to do that. And I basically just borrowed what he explained on that video that he created on multitasking to be able to perform multiple tasks on the updated prototype circuit that we created here for the OwlBot project. So that was very helpful to be able to get these items to occur and fire off and work all at the same time. So we've initialized the two time intervals, time interval 1 and time interval 2, to use in our code later. We want to use these for their specific predetermined times that we created as time intervals for how long the solenoids will activate on and off. So these values can be adjusted and changed to your preference. And I just happen to choose 250 milliseconds and 750 milliseconds. Moving on to the next part of the code that's new since the last time we've updated it is this new variable called Propeller on line 76. It is initialized to be equal to 9, and the Propeller variable represents the digital pin 9 on the Arduino that we've hooked one of the leads of the DC motor to. And we'll use this variable in code later to control when to turn the DC motor on and off. So looking further in the code, we've added a few new pin modes for these new variables that we created for the left wing, right wing, and propeller variables. We've initialized them to each be an output. So both the left wing and right wing variables represent the solenoids, as we've mentioned before, and they will be receiving output signals from the Arduino to activate or to turn on when needed at pins 7 and 8. And the propeller variable that represents the DC motor's propeller on its shaft will also be receiving output signals from the Arduino to turn on when needed at pin 9. Looking further down in the code on lines 94 through 96, we've created these new digital rights for the left wing, right wing, and propeller variables that we've created in this part of the build series. We've initialized them all to be low because when we first run the code, we don't want the wings or the solenoids to automatically be activated and start moving as soon as we turn on our circuit, and we also don't want the propeller on the DC motor to start spinning once we turn the circuitry on. We only want the solenoids and the propeller to be on when motion is detected by the peer sensor. So that's what this is for. So if we look inside the playowl function farther down into our code, we've updated that playowl function that we created in one of the previous coding sessions that we had for the OwlBot series. And here it says that if you look inside the playowl function, we can see the call to the blink eyes function is made. We created this function ourselves back in part 3 of the OwlBot project in order to get the 2 red LEDs we installed on our prototype circuit to blink when motion is detected by the peer sensor. So now let's go ahead and look inside the blink eyes function next. So the only reason why we're looking at this playowl function is because we see that in that function we created a call to the blink eyes. So really, I mentioned earlier that we made an update to this function, playowl function, but we didn't. All we're doing right here is looking that previously we were making a call to blink eyes function, and we want to look at that specifically for this part of the build because we've updated something in the blink eyes function. So we just want to remind you here that in the playowl function, when it's called, inside that function, the blink eyes function is called, and when we go in code to the blink eyes function, there's something new happening on in here. And this function contains a pair of for loops, as we can see here. This whole section here, we have 2 for loops here, one inside another, that allows us to create the illusion of the OwlBot having blinking eyes. We can see that we've modified the second loop and that it now has a local variable called current time initialized within the loop. We use this to return the number of milliseconds passed since the Arduino board began running the program. So you can see this variable called current time here. It's initialized to millis. And again, we're using this to return the number of milliseconds passed since the Arduino began running the current time. Looking farther down into the explanation here, we see that next we use the digital write function to turn both the left and right eye, the two LEDs of the OwlBot, then wait for 1/8 of a second. Whoops. So if we look here, we see that there's a digital write to the left eye and to the right eye. We're doing a digital write for them to be high or turn them on, and then there's a delay, or we wait for 1/8 of a second. 125 milliseconds is equivalent to 1/8 of a second. Next, we see that two statements follow. The first if statement looks to see if the difference of the current time and previous time 2, or prev time 2, is greater than time interval 2. And if it is, then it's to call the spin propeller function, which we'll see later is a function created to tell the Arduino to turn the DC motor on to spin the propeller on the shaft of the DC motor. So that's this part here, this if statement. If current time minus the previous time 2 is greater than the time interval, then we want to call the spin propeller function. These are all new variables that we've created here in part 5 of the build series that we just discussed about. And we then set the previous time equal to the current time to use again later when the blink eyes function is called again. So that's this part here. We set the previous time equal to the current time. Once we call the spin propeller function and we exit that function, we set the previous time to the current time. And then it goes on to say that the second if statement looks to see if the difference of the current time and the previous time 1 is greater than the time interval, and if it is, then it's to call the flap wings function, which we'll see later is a function created to tell the Arduino to turn the solenoids on that will act as our mechanical motion to flap the faux wings or fake wings we'll create for the plastic owl figure we're using in a later part of the OwlBot project series. And we can see that if statement here, and if this statement is true, then we call the flap wings function, and then it says, just as the previous if statement, we then set the previous time 1 equal to the current time to use again later when the blink eyes function is called again. So that's this part here. And then we see lastly in the blink eyes function, we call the digital write function for each eye LED right here of the OwlBot to turn off. So that's these low signals here. We're wanting to turn both the left eye and the right eye off. And then we want to wait or have a delay of 1/8 of a second, or 125 milliseconds, before the program leaves the second for loop, as we can see here. So moving along, now we want to look at the spin propeller function. And again, the spin propeller function is called within this second for loop in the blink eyes function. And it's called if current time minus previous time 2 is greater than time interval 2. Then the spin propeller function is called. And the spin propeller function is called, like I just said, when the within the blink eyes function. And when it's called, its only job is to turn the DC motor high or on, followed by 1/4 of a second delay. Then it turns the DC motor off or low, followed by another 1/4 second delay. As you can see in here, it turns it on high or on. We wait 250 milliseconds or 1/4 of a second. then we turn the propeller off or low, and then we wait another 250 milliseconds or a quarter of a second. And you can change these to whatever you want. I just happen to choose 250 milliseconds. And then we want to take a look at the new flap wings function. And again, that is called from this second for loop within the blink eyes function. And it's called if that current time minus the previous time 1 is greater than the time interval 1, then it's, if that's true, if that statement is true, then it calls the flap wings function. And the flap wings function, when it's called, its only job is to turn each solenoid on or high, followed by 150 millisecond delay. Then it turns each solenoid off or low, followed by another 150 millisecond delay. And you could see that here within the flap wings function. We turn the left and right wing on or high. We wait 150 milliseconds. And then we turn the left and right wing off or low and wait another 150 milliseconds. So that's pretty much all that we've added or updated to the code since the last time we updated the code back in part 3 of the OwlBot project build series. And again, you can see the entire code here from the website, or you can go to our GitHub page by clicking here, and I'll leave the links to our website page for the code and to our GitHub page in the links in the description in this video below. So next, once we've got our code all updated, we need to compile it and upload the code to our Arduino, which means that we need to connect our Arduino to our computer, compile it, upload it, and then disconnect our Arduino, and then we just want to test and see what we've done. So we ended up adding the solenoids to our prototype of the OwlBot project. We add a DC motor to our with the propeller to our prototype of the OwlBot project, and we created the code. We verified the code and we fixed any errors. We compiled and upload the code to Arduino, and then we just disconnect the Arduino from our computer. And then once we've compiled it and uploaded the code to the Arduino, then we can test and see if everything works. And next, I'll show you the working circuit that we have thus far, this part 5 of the OwlBot project series. So let's take a look at our prototype circuit working once we've already compiled and uploaded this updated code here in part 5. So let's look at that next. That's pretty cool, huh? I mean, we've gotten pretty far so far in this OwlBot project build series, and we're that much closer to getting our OwlBot completely finished. I mean, we've only got a few more steps left, and we're getting pretty close to the finish line. So I'm getting pretty excited about that, and I hope that you are too. So what's next for the OwlBot project build series? So far, we've implemented motion sensing, sound, flashing LEDs, and now we have mechanical motion with the use of a couple of solenoids and a DC motor. Now we need to have a way to control turning everything on and off, a master switch, if you will, for the entire circuit. So next, we'll need to add a switch for each power supply being used for our circuit to be able to control the power to our circuitry. So this is what we'll be doing in part 6 of the OwlBot project. I don't know about you, but I'm having a whole lot of fun building this OwlBot. I mean, it's taking a pretty good while. It's been several months in this project, but you know, with the patience and determination and the grit that we have performing this project together, I know that we can finish it and it'll end up working. And hopefully we can get it working pretty flawlessly. It's pretty exciting at this point. We've got all the stuff that we've wanted so far to work in our project, so hopefully the rest of it will go pretty smooth for us. So I want to thank you for participating in this project. I hope that you've enjoyed the build thus far, and let us know what you think. Just leave a comment, and I'd like to hear from you. I'd really like to hear from you if you're been building this project and been following along this whole build series. That'd be really neat. So again, I want to thank you. I hope that you've enjoyed the builds thus far and hope that you stick around for more. Remember to keep at it and stay motivated. And until next time, let's watch our accomplishments so far. I'll see you next time. Take care.